Hello everybody and welcome to the 10th lecture of MHM 420 780 MUA 782. In our last lecture we talked about condensation. We just did a little bit of like a mathematical manipulation of some kind of correlation to find the Nusselt correlation. But basically what we said that for condensation and vertical surface we have three different regimes. We have laminar or wave free when the Reynolds is between 0 and 30. The second one is laminar but wavy when the Reynolds number is between 30 and 1800. And the third one is when Reynolds is higher than 1800 and we call it turbulent. For different regimes, like there are some for different regimes, different researchers suggested some semi-empirical or theoretical correlation that we are going to use in this chapter of the textbook. You can find it in your textbook for condensation, so you don't need to remember anything. You just need to know how to use them. You can go to your textbook, open it, and after that use it during the exam. So first we start with wave free, Reynolds bit lower than 30. As you can see here, there are two correlations that you can find H vertical based on the Reynolds, and after that those properties. We talked about the condition. We said that how you are going to read it from the table, so it's clear. If the regime is wavy, which Reynolds is between 30 and 1800, those three correlations that you can use. And if it's turbulent, there is another correlation that you can use to find H and Reynolds. So basically that's it. It's not it's very simple, like three sets of correlations that you can use, but of course it's based on the Reynolds number that you are dealing with. What we were talking so far, they were all about the vertical plates. We talked about those correlation, the proposals for each of the flow regimes associated with vertical plates that were suggested by different researchers. But now let's talk about inclined plates. What will happen if we have an inclination angle? If the theta or inclination angle is low, it's lower than 60, in wavy or wave free, we can just use a very simple correlation, and we say that each H inclined is equal to H vertical multiplied by cosine theta to the power of 0.25. So basically, by using a very simple correlation, we can calculate the H when the plate is not vertical. But there are two options. Two conditions. First is inclination angle should be lower than 60. Besides that, the flow should be wavy or wave free. It's a very good approximation, and we don't need to go through very complicated calculations to be able to find the H for inclined vertical plates. But we talked a lot about condensation, but let's solve one example and see how all those knowledge can be put into practice. So there is question 10.60 of your textbook. Let me just create some free pages to be able to start solving. Yes, here. Okay. Saturated steam at 1 atmosphere condenses on it, so the size of the vertical plate, maintained at 90, circulating the cooling water through the outer side. It's asking us to determine three different things. First, the rate of heat transfer by condensation to the plate. B, the rate at which the condensate drips off the plate at the bottom. Assume wavy laminar flow. Is it a good assumption? So first we need to use the wavy laminar flow assumption. After that, find the Reynolds, and if the Reynolds is between 30 and 1800, so is wavy laminar, so it was a good assumption, otherwise it was not. And the C is asking us to find the rate of heat transfer by condensation to the plate, and D, the rate at which the condensate drips off the plate at the bottom when, for the case of the plate being with the inclination angle of 60 degrees. So let's start and see how we can sort it out. So first they said that assume wavy laminar. So for wavy laminar, we know that the Reynolds is equal to Reynolds of vertical wavy is equal to 4.81. How we find it? This correlation. We are going to use this correlation to calculate the Reynolds. Just write it down there. 4.81 plus 3.7 LKL T sat minus TS mu L Hfg plus modified one GL to the power of 1.3 divided by 0.82. Sorry if I didn't write it nicely, but it's the same correlation as here. So it's the same correlation. So what we need to do is first we need to we go to the table and we find the property. We said that for condensation the majority of the properties are being read as film temperature beside Hfg and rho v, which should be at saturation temperature. So let's start. Saturation temperature T sat is equal to 100, then 100 we go from the table, so Hfg is equal to 2257 10 to the power of 3 joule kilogram. OV is equal to 0.60 kilogram 3. But for T film, which is 100 plus 90 divided by 2 is 95. Table A9. So we read rho L, mu L, VL, which is UL divided by rho L, CPL, and KL. Okay, so we read these numbers at temperature that we said. If we don't have it, we interpolate. After we have all these numbers, the first step is calculating Hfg modified. We have the Hfg, so plus 0.68 CPL T sat minus T surface, so the answer will be 2.286 10 to the power of 3 joule kilogram. There is something that lots of people make mistake. You need to keep in mind that sometimes when you read it from here, you might table is based on kilojoule. Okay, but here, so CP sometimes is for based on joule, so it's 4212 joule kilogram Kelvin. So give a very like a detailed attention to the units, because some of the times like a student make mistake, and after that when you add two different values, which is this value and this value with different units, you end up everything is wrong. When Hfg is wrong, Reynolds is wrong, H is wrong, and everything will be wrong. So now we have the modified Hfg, we have all the rest of properties. So Reynolds will be 1113. So we assumed that is wavy, so Reynolds is between 30 and 1800, so our assumption was correct. We proved it. Now that we are sure that the Reynolds between 30 and 1800, there is like a correlation here. We have the Reynolds, we have all the properties, so easily we can find the H vertical. So by using that vertical, and for wavy, I'm not going to write the correlation, you have the correlation there, so the answer will be 6279 watt per Kelvin. Now the second one, what is asking us is asking, okay, the rate of heat transfer by condensation to the plate. So rate of heat transfer, we know that rate of heat transfer is watt units, so Q dot is like HAS T sat minus TS, so the answer will be 1507 kilowatt. Okay, so this is the first one. The second section is asking the rate at which the condensate drips off the plate at the bottom. So basically it's asking us for m dot condensation. Station is Q dot Hfg, but start the modified one, so it will be 0.659 kilogram per second. The question is also asking that do everything the same, but when the plate has like a 60 degrees inclination angle, we said that since it's wavy laminar and Reynolds is between 30 and 1800, it was another condition, as you remember. Yes, theta, if it's smaller than 60, we can apply the very simple correlation that H inclined is equal to H vertical, that cosine theta to the power of 1 divided by 4. So if we implement that one, so for Reynolds will be the same, but for H will be the same as well. So first from the Reynolds will be 920.8, 60, H will be 60 will be equal to 5198 Kelvin. Q dot 60 is equal to 1248 kilowatt, and M dot condensation 60 is equal to 0.546 kilogram per second. But if you compare it, you see that H is lower, Q net heat transfer rate of heat transfer is lower, and even the M dot, or the fluid, the produced fluid, is lower than vertical plate. So basically that's the information that we are going to receive from solving it for vertical and at the same time for inclined one. But let's say we wouldn't start from the correlation related to wavy laminar. So we didn't know, we had absolutely no idea. If we would have used different correlation, because here was saying that first assume wavy laminar and after that if it's a good assumption. So basically question was made it very simple for us to suggest that first assume that it's wavy laminar, and after that if it's not working, go and try the other one. But in reality you might end up with a question that you don't know anything about it, and you want to first start with the no wavy, after that wavy free, and after that turbulent. If you would have started with no wavy, Reynolds for no wavy would have been 865. So immediately you could say that the Reynolds is much higher than 30, so then it's wrong. It can't be no wavy. Reynolds of wavy free we calculated, which was 1113. Reynolds was between and which was right, and for turbulent the Reynolds number would have been 72. Reynolds is wrong. So you can see that even you could not use no wavy or turbulent. So it was a good assumption that you start from wavy laminar, but basically it was not an assumption. We started because the question was asking us to do it, but sometimes maybe question never asks you anything and says that okay, you find it yourself. So you calculate the Reynolds for three different condition, and you see in which of them the Reynolds value is in the same bracket or bracket for no wavy or wavy laminar or turbulent Reynolds numbers. And as after that, when it's basically correct, at the end you can say that I assumed that it was, let's say, no wavy, and my assumption was right. I assumed that it's no wavy, my assumption was wrong. I assumed that it's wavy laminar second time, and it's correct. Okay, now let's talk a little bit about vertical and horizontal tubes, because we were talking about just like a plates. So vertical tubes, for vertical tubes under laminar regime, wavy free or wavy laminar, we can use vertical plate correlation. So vertical, basically vertical plate, vertical tubes, we said that if it's wavy, wave free or wavy laminar, vertical tubes can be assumed as vertical plate. So basically for these two is saying that when the Reynolds number is lower than 1800. Horizontal tubes and spheres. So the average heat transfer coefficient for film condensation on the outer surfaces of horizontal tube can be calculated by this correlation here, as you can see. And for spheres, another correlation. The only difference between them is the this constant number. The figure on the right shows horizontal tubes stacked on top of each other, which is very common in condenser design. The average thickness of the liquid film at the lower tube is much larger as a result of condensate falling on top of them from the tube directly above. So the average heat transfer coefficient at the lower tubes in such arrangement is smaller. The average film condensation heat transfer coefficient for all tubes in a vertical arrangement can be expressed as the same as horizontal tube, but instead of D, we can have ND. So as you can see here is N just was added. We can also use this correlation as well when N is the number of horizontal tubes. Now the question is why we bother ourselves to learn about different tube positioning in condensation. Why we should know about horizontal tubes, vertical tube, or inclined tubes or plates. Because we want to see which one has the highest heat transfer coefficient to design based on that. So shape and geometry plays a very big role in condensation. We want to find correlation for as much geometry as we can, because that will help us to have a better understanding what geometry, what like a kind of configuration, and what Reynolds number will give us the better heat transfer performances. Okay. A comparison between a vertical tube of height L and a horizontal tube of diameter D yields to this relationship, which is maybe it's very nice to just compare which one works better. H vertical, H horizontal, 1.29 dl to the power of 4, 1 divided by 4. So if we set H vertical is equal to H horizontal, then L should be equal to 2.77 d. So it means that if length of a tube is 2.77 times of its diameter, the average heat transfer coefficient for laminar regime will be the same whether the tube is positioned horizontally or vertically. So you see, simply from like some just kind of correlation, we got a very good design points. We also realized that for L greater than 0.277 diameter, heat transfer coefficient is higher in horizontal position. So in most of practical applications, length is higher than 2.77 times of diameter, so it is common practice to place tubes in condenser horizontally to maximize the condensation heat transfer. Okay, so that's why we try to use these calculations and all those correlations, because we want to design something based on the fundamental of heat transfer which has a better performance. Before speaking about the film condensation inside the horizontal tube, we need to talk about the effect of vapor velocity on condensation. So far, I mean, in all calculations I introduced to you, we assume that the vapor velocity is small, so the vapor drag is negligible, which is usually correct, and it's the case. But when the vapor velocity is high, vapor will pull the liquid at the interface, since vapor velocity should be the same as liquid velocity as the interface. If the vapor flows downward, the same direction of the liquid, this additional force will decrease the film thickness and will result in lower thermal resistances and higher heat transfer. So you can see I've showed it in the picture, but let me just remove this one. First show the picture, after that this correlation here. But you see that when the vapor velocity is low, there is completely different behavior. This I think, if I'm not mistaken, Chato in 1962 proposed a correlation for internal condensation heat transfer coefficient when the Reynolds of vapor is lower than 35,000. So just this correlation is for Reynolds than 35,000. So first you find Reynolds of vapor. If it's lower than 35,000, you can use Chateau correlation. Now you might ask what temperature I should read rho v and mu v here. So the same as other condensation correlation in saturation temperature. Always rho L is read at fin temperature and rho v at sat temperature in condensation. Okay, I think that's it. And last thing that we need to discuss is drop-wise condensation. This figure clearly shows the meaning of drop-wise condensation. Let me just move correlation a little bit, or let me put it up. Countless droplets with different diameters covering the whole surface instead of a continuous liquid film. If you remember, I mentioned that heat transfer in this case is much higher compared to the film. Boiling for condensation is the same. Why? Because when we are talking about the film of liquid, it means that a very high thermal resistances. So we would really like to have the drop-wise condensation, but the problem is achieving drop-wise condensation is very difficult because needs lots of surface treatment, and at the same time there is no guarantee that you can always get the drop-wise condensation. Griffith in 1983, after some experimental investigation, proposed the empirical correlation for drop-wise condensation on copper surfaces, but normally we use it for the rest of material as well. So as you can see is if Tsat or saturation temperature is higher than 100, basically is a simple number, so it's constant. But when the saturation temperature is between 22 centigrade and 100 centigrade, there is like a simple correlation to find the H, which is condensation heat transfer coefficient of drop-wise condensation. I think basically that's it. I covered all the important aspects of condensation. We talked about different regimes. We said that if we have wave free, when the Reynolds number is lower than 30, we have laminar wavy when the Reynolds number is between 30 and 1800, and turbulence when Reynolds is higher than 1800. But now let's solve one or two examples. Let's see how much time we have to understand better what's happening in condensation. And I think maybe we have enough time for two examples, but let's first start with the first one. A 5.5 meter long vertical tube is used for condensing saturated steam. We have the temperature of steam 60 degrees, surface temperature of the tube we have at 40. Determine the heat transfer rate to the tube and the required tube diameter to condense 12 kilogram per hour. So we have the m dot of steam during the condensation process. Assume wavy laminar flow and that the tube diameter is large relative to the thickness of the liquid film at the bottom of the tube, and is asking us to show or discuss if those assumptions are good assumptions or not. Okay, first we start with the assumption of wavy laminar flow. So we write the correlation for wavy laminar. If we write the correlation for wavy laminar, we know that there are some properties that needs to be read. I said that just Hfg and rho v are going to be read at saturation temperature. The list of the rest of properties needs to be read at film temperature. So let me just write it down here. Hfg and rho v at sat temperature, saturation temperature. The rest of properties must be read at film temperature. So what is the film temperature here? 60 plus 40 divided by 2 is 50. From table A9, saturation temperature 60. So first we find the modified Hfg. I just write the answers to just like help you a little bit. Please do it at home to make sure that you are getting the same answer as me. 2.416 10 to the power of 6 joule per kilogram by using the Reynolds for vertical wavy. Use the correlation. I'm not going to write the correlation here. 454. So we assume that is wavy laminar. Now 30 Reynolds 1800. Okay, the assumption was correct. We have H, so we have Reynolds, we can find H, we have all those properties. So vertical, H vertical and wavy is equal to 4937.5 watt square meter per Kelvin. The rate of heat transfer to the tube during the condensation process. So Q dot is M dot Hfg modified one, which will be 8053 watt. Heat transfer also can be expressed as Q dot is equal to HA T sat minus T surface, which will be H pi dl T sat minus Ts. So then finally D is equal, because it's asking us for D, is H pi L T sat minus T S divided by Q dot. Then D will be equal to 0.0173 meter. To verify the assumption, because if you remember, it's asked for another assumption. First said that assume the wavy laminar flow. We assume that we solved it's correct, and it's asking that also assume that the tube diameter is large relative to the thickness of the liquid film. So now we have the diameter, so we need to find the thickness as well to be able to say if it's relatively small to it. So you see, tube diameter, we have it, but we need to find the thickness of liquid film, or delta, to compare these two together. So delta, if you remember, we mentioned that is 4K L divided by 3H, so is 1.79 10 to the power of minus 4 meter, which is much smaller than 0.0173 meter. So this assumption was correct as well. Yeah, I think that's it. Basically, there is nothing else to be added to this example. But please do try to do it at home to understand what's happening, because it's very important to do it with yourself and to see if you can receiving the same answer. Because in practical, in principle, it's very simple. The only thing that you need to do for condensation or even boiling is finding the right regime. In boiling, if you remember, it was like delta Tx's. Here is Reynolds. So based on the Reynolds number, you just go and find the right correlation. You go to the table beside Hfg and the density of vapor, which you rate them at saturation temperature. The rest you rate them at film temperature. You write them. You again write the correlation. You put those numbers that you read from the table into the correlation. You find the Reynolds. You double check it if your first assumption was correct. If it was correct, you continue with the calculating H, and everything else will go the same as example that I solved. There are another ways to sort it out as well, because you can see that it can be added to the heat exchanger concept, and you can mix different concepts into it as well. But don't panic. It's very simple. Just follow the same procedure and everything will be fine. Even I think it's more or less will be like question 2 of the test 1. Maybe lots of you might were thinking that is very difficult, but I'm sure when you saw the memo, you realize that how easy the exam was. How easy the test was. So I think that's it. It's the end of our 10th lecture, and enjoy the rest of your day, and please try to do all these examples at home one more time to make sure that you are getting the same answers. If you have any problem, please join to the Google meeting, and after that you can ask any question that you might have. Okay, bye bye.